Today, we're going to be talking about Azure SQL Data Warehouse, and the title of the session is Dining on Data. One of this is a bit of a private joke in the product team, mainly because the release that we have actually announced on Monday, which is this new Optimized for Compute tier, the project internally was called Project Pesto for petabyte storage, and so everything tastes better with pesto was where the genesis of the title came from. Today, what we're going to be doing is talking about the new performance tier, what it means to you as data warehouse professionals and building data warehouse and advanced analytic solutions, and how you can make the most of that solution in your workloads. And then what we'll then focus on is then how you can then take advantage of it to maximize performance, what you can do as professionals to make the most of the solution that we are providing. At the end of the day, SQL Data Warehouse is a platform for you to bring your data workload analytical solutions. There will be a number of SQL Data Warehouse talks from the product group this week. I strongly encourage you to go to all of them because today we're going to be covering a very kind of focused area, and different sessions throughout the week will cover a broader spectrum of the solution itself. Okay, now we've got about 75 minutes this morning. If you have questions, if you could hold them to the end, I will try and save some time at the end. Please come and make use of the microphones at the front, and we'll make sure to answer your questions. If you want to speak to me afterwards, I will be actually in the booth at the SQL Data Warehouse booth, both today and tomorrow lunchtimes. You are most welcome to come and speak to me or to any of the product group that's there. We'd be delighted to answer any questions that you may have about the service or anything of that nature. So without further ado, let's just talk about performance tiers, because this is something that's kind of new to SQL Data Warehouse all up. We haven't had kind of the notion of performance tiers in the past, but we have introduced them with the announcement on Monday to help customers differentiate their workloads and pick a solution that works best for them based on their specific requirements. And so to help guide you through that decision-making process, that's what this session is, one of the primary objectives for this session. So the first thing is, if we talk about the first performance tier that we have, and we call this Optimized for Elasticity. This architecture is the architecture that we have that's generally available today. All we really have done is named it and given it a name as a performance tier, and that performance tier is Optimized for Elasticity. Now, as you can see on this diagram, what we have done is essentially been able to separate the compute and the storage in our architecture so that when you are using the system, you can scale independently of either the storage or the compute, i.e. you're not having those two elements are not combined into one unit. Typically, when you buy data warehousing products, your unit of storage and your unit of compute are tied together, which means that if you have demanding compute workloads, you're paying for more storage, or if you have more storage needs, you're overpaying on compute. Now, compute is of the two things, is actually by far and away, the more expensive of the two resources. You think about licensing, you pay by the core. So having something that separates those two elements is very helpful. In our architecture, we have a control node because we are a single master system, and when you connect, you connect to the control node, and then that work is pushed down from the control node down into the compute nodes, and the compute nodes then process the data against the remote storage. We hold the data in remote storage so that we have that physical separation. Now, in SQL DW, we also support the notion of row stores and column stores. And in SQL Data Warehouse, you can choose which you would like to use. We default you to column store because columnar storage is the kind of go-to kind of storage model for the vast majority of data warehouse workloads, but you still have that flexibility and choice to use whichever you prefer. As we move through, you're going to see more and more reasons why you're going to want to use the columnar storage as we explore this session. Okay. Now, in DW, we also take snapshots and backups. They're all kept on remote storage as well. So the storage, the compute units themselves are there and available for you whenever you want them. Now, this does introduce some interesting capabilities for us. The first of which is that we can scale the compute on demand. Right? That means that you can increase your compute and decrease your compute as and when you want to, and it takes on an idle system, say 90 seconds or so to get through and reallocate the compute to the storage. Okay. Now, this is what we call an elastic operation. It's an elastic scaling of the system, and it's only possible because the compute and the storage are separate. Another elastic operation that we enable you to do is pause the system. This is where you effectively completely deallocate the compute that is attached to your system. By pausing the compute, you are completely separating and removing the compute essentially from your build. So if you think about data warehouse workloads that maybe do a lot of work and then they push the data out to data marts and is then not queried for the rest of the day, this is a phenomenal cost saving for a number of those types of solutions. Right? Now, obviously, if you're going to be able to pause it, you're going to want to bring it back. And so we also support the notion of a resume. The resume brings back the compute that you had previously allocated and brings your warehouse back online. All of these operations are essentially on-demand operations, and you can run them frequently. So the point here is that by separating the compute and storage, you're able to get support burst-type scenarios. You're able to support scenarios where you have only a need for compute at certain times of the day. You're completely in control of when and how much compute you are using at any given time. Right? Now, what we announced on Monday was a new performance tier called Optimize for Compute. When speaking to our customers and working within Microsoft itself, one of the things that we learned is that actually a lot of customers actually were pushing the boundaries of compute significantly. Right? They were running very demanding computationally intensive workloads, and we're going to look at one in particular as a case study kind of example. And what they were doing was they were using the warehouse very extensively throughout the day, and so they weren't using as much of the elasticity of the warehouse, but what they were doing is driving significant resources. So what we have done is we've built this new performance tier called Optimize for Compute that uses the latest generation of hardware in Azure today, that leverages a new NVMe flash, which is basically straight off the PCI-style interfaces. So you are getting maximum bandwidth through that SSD layer, and we create a caching tier on the compute node. Now, this is very important and creates great value because when you separate compute from storage, you basically make a remote I/O operation in your warehouse. So that remote I/O is going to have some kind of time penalty to it, and so for very compute-intensive workloads, that becomes an expensive cost. So what we enable with the optimized for compute layer is the ability to move column store segments up into the cache on demand to create a local copy of the data in the caching tier so that you are not using remote I/O operations. Now, the data is still separated compute and storage. This is just a copy of that columnar data that we hold up on the cache tier for you to facilitate this. The nodes themselves are also much bigger in size, both in terms of cores and memory and all that sort of stuff. So the compute that you're using is much more significant. But equally, the throughput that you can get is really quite dramatic. And we've seen individual queries running like 10 times faster just by going through this process. The other thing that this solution does is it actually makes an interesting change in the storage layer as well. The columnar data is not actually is actually physically separated from the actual SQL Server data files under the hood, and the actual columnar data is held independently on remote storage. This enables us to actually hold an unlimited amount of columnar storage data, and that columnar data is what we move up into the cache. Okay? Now, when we're doing this, what we're essentially doing is tiering our compute with the storage itself. And we're creating a local cache on those compute nodes. Now, the physical memory is going to be the hottest part of the cache. Okay? Just like in anything else. We have a separate kind of pool of memory that we're using for these columnar segments. The second kind of order of in the cache is that NVMe SSD. And we can hold a significant amount of your data, the columnar data, locally in that caching tier. Okay? So that gets you another hit before you even go out to the remote storage. The remote storage is unlimited. It's a bottomless pool. It's the coldest part of this data, but it's still warm in that as much as the data is online, it's still available to you. You can query it just like as you would before. The hotter the data is, the faster you will go, obviously. But the key point is that you're not having to kind of run any kind of archival solutions or anything like that just to be able to access the data in the most frequent way. One of the most interesting elements of data warehousing is that ultimately we are tracking data over time. And if you think about, in most cases, when we think about businesses and their utilization of that data, they're actually most interested in the hottest part of the data. They're most interested in the current week, current month, stuff like that. However, in data warehousing, you will also get a much lesser requirement, but you will get it quite frequently, is that notion of like a like-for-like type comparison that may go back years of data. Having that data available and online that's just in an ad hoc queryable form is incredibly valuable. Now, we are also seeing in the world today lots of advances in the worlds of data and AI, which is driving customers to run more and more computationally expensive queries. They are doing this using SQL because of the nature of the language. It's an incredibly accessible language. It's still one of the most pervasive languages across every single kind of skill set, right? Whether you're a data analyst, business analyst, all the way through. So without any training, customers can give get rich insights straight from that platform. Okay, so what we're seeing is customers wanting to do more and more advanced analytical style queries using SQL Data Warehouse, which is great for us, and it's great for them, because what this solution brings to them is the compute that they can run to perform any of their kind of calculations. Okay, and we're going to look at that in some detail as we go through our case study. Right. So, in order to enable that, one of the things that we have done in the Optimize for Compute tier is dramatically increase the amount of scale that we have brought into the system. Okay, so there is 5 times the amount of compute available to you in the Optimize for Compute tier versus the Optimize for Elasticity tier. The Optimize for Compute tier starts at 1,000 compute data warehouse units. We use a slightly different unit of measure, and that translates onto your bill as a single line item. Okay, we start at 1,000 compute data warehouse units, and at preview, when that is fully released in the fall, the preview price on that is about $6 an hour. You can scale that on demand, and I'll show you how in a second, all the way up to 30,000 compute data warehouse units. And so you can see at preview, that's at about $180 an hour. Now, contrast that to the Optimized for Elasticity. Optimized for Elasticity starts at a much lower price point. It starts at $1.21 an hour, depending on your region, and you go up through there all the way up to about 6,000 data warehouse units. Okay, and we find that for a lot of customers, this works absolutely great. They love the frequent scaling on the burst capabilities, and they are kind of using that elasticity to drive a different type of data warehouse workload than they have before. However, for the customers that we are coming to us looking for more, the compute scale that's available over here on the right in the Optimized for Compute layer is the way to go. As I say, it has 5 times the amount of compute capability. Now, it's interesting, 5 times seems to be a bit of a recurring theme when we work at this. So when we look at the storage scalability, when we look at on the left-hand side, Optimized for Elasticity currently supports 240 terabytes of compressed storage at the remote layer. And that compression primarily is driven by column store. And typically, when we're using column stores, we can drive something like a 5x compression. We've definitely seen more. We sometimes see less. But as a typical guide, we kind of come in at 5x. And so you can drive on the Optimized for Elasticity, you can have, in terms of raw data, about 1 to 1.2 petabytes of data in that solution, okay? Which is still a pretty material amount of data for most customers. Now, you contrast that to what we're able to address and achieve in our Optimized for Compute tier. Because we have separated that columnar data out and hold it independently in the remote storage, we're actually able to literally hold an unlimited amount of that data. Okay, so I've just put the scale in there for you against the row storage, because you can still hold the 1.2 petabytes of raw data in row storage, right? But the columnar data is effectively unlimited for you. Okay, so here are our performance tiers. We have our Optimized for Elasticity, which is currently generally available and available in 33 regions in the world. It is the most broadly available a cloud data warehouse solution in any cloud platform, and it has been broadly adopted throughout the last year. Okay, now we are just about to unveil the preview of the Optimized for Compute tier, and this will be available in 6 regions to begin with, and we will grow that over time, and based on customer demand and feedback, we will grow that into new regions as we go. All right, so price points, similar, as I just said, $1.21 an hour to start with on the elasticity, and $6 an hour preview for the compute range. Okay, now the starting scale is obviously much lower on elasticity, which can mean that for some customers wanting to do dev and test, that may be a great solution for them. But as you can see, the language surface area is the same in both products, so there's nothing to stop you doing like dev and test in elasticity and then using Optimized for Compute for production scenarios if you want to optimize in that way. There's no reason why you couldn't do that for like functional testing and validation and initial development. The starting point for the compute is at 1,000 compute data warehouse units, okay? And the maximum scale is, as you can see, 6,000 data warehouse units for elasticity, 30,000 for compute, and that storage there we just discussed, so we won't go over that again. The scenarios around elasticity are really where what you might see a customer who was maybe thinking of running something at the higher end in elasticity, let's say 2,000 data warehouse units. If they really want to be able to burst scale versus the incrementally scaling, then that's a good scenario where a customer may still choose to run with the elasticity option today. That's because a cache is something that is filled on demand as queries come in. So you go through that process of warming the cache. Whereas in elasticity, because everything is remote, the performance is immediate. Okay, and you see that benefit immediately as you scale. And so if your workload is such that you want to be able to scale and just go straight into it with your workload, then you are going to much more likely prefer the elasticity approach versus the compute option. The compute option still supports all of the elasticity operations, but there is a process, a period, certainly in preview, where it takes a bit of time for the cache to re-warm up after a scaling or a pause and resume. Now, one of the things I did mention at the beginning is that those nodes that we're using, the compute that we make available to you in Optimized for Compute, is significantly larger. That you can see in the memory utilization here. In a query, we roughly give you about 2.5 times the amount of memory per query. So that's a great benefit for a number of customers. It actually means that you have to do less kind of management of the memory in the system. And because we're an MPP system, we are very much targeting these bigger data warehouse kind of queries, exploratory analytics, and deep computation type queries, as opposed to kind of rifle shot here, there, and everywhere transactional style queries. And so we actually allocate quite a bit of memory, whether you're in elasticity or compute, to make sure that you have the resources that your query needs when it's running. Okay, so that's basically it. Now, what I wanted to do is to flick over to my demo machine, and where I'm going to just give you a highlight. You can't actually see this today live. It actually is kind of blocked, but I wanted to try and show you what the experience is going to look like, so that when it is available in the fall, it will be of no surprise to anyone in the room. Okay. So here you can see that I have logged into the Azure portal. And to create a SQL DW instance, all I need to do is hit the plus new button, ask for the SQL Data Warehouse blade, and then I can create a database name, and we'll call it Ignite 2017. I pick my subscription. I will use my Visual Studio subscription, and I will pick a resource group, or I'll create a resource group. Resource groups are very useful, especially for managing and containing everything within a given solution. It also makes cleaning up your mess afterwards very easy, because you can delete at the resource group level. So if I create my Ignite Data Warehouse, Ignite server, okay, servers are important. They are a logical construct, but we use these for actually also zoning you to a location or a region within Azure. You can see here I've picked West US 2, which is one of the 6 regions available for the Optimized for Compute performance tier. When I click Select, it closes the blade, and the performance tier situation is open. It's cleared it. It's refreshed. I apologize. This is the experience you're going to get if you were to log in today. I'll go and see if I can get it fixed in a second. So you can see that as you scale the system, you're increasing the amount of compute, and we put some safeguards in the system to make sure that you don't accidentally over allocate your performance. Okay. Now, what you will be able to do is to click on this extra tab here and be able to move over. If I get a chance, I'll try and get that running for you. Right. Okay, so the regions that we will have available for preview are East US, East US 2, West US 2, South Central US, Western Europe, and Southeast Asia. Okay, so that's they're the regions that we will have available at the to begin with. And as I say, based on customer feedback and demand, we will add more regions as we go, and would look forward to doing that as we go. So I'm just quickly checking to see if I can get the blade open. So if you just give me 1 second, I'll just check that. So there you go. So when you click into the preview portal, you'll see that you're able to scale the system just like before. On the left-hand side, you see you've got a block here that's specifically targeting the performance of the system. And as you can see, as I scale, I'm increasing. You notice there's this information box come up here. This is just because as you start going up these levels, you don't want anyone inadvertently kind of provisioning something that was too large. We want to make sure that you know it's available, but at the same time, we want to make sure that it's a deliberate, not an accident. So once you actually scale the system, you can join the preview automatically by just coming along, clicking this, sharing your name and email address so we can reach out and work with you during the preview. And then you'll literally finish the blade and click create, and it will be done. Okay? Okay, so that's basically what the optimized compute tier is. What we're going to talk about now is a scenario about why we have this and why things like SQL Data Warehouse and optimized for compute are important, and why they mean a great deal to our business, both inside Microsoft and outside, to you as our customers. So at Microsoft, we have a multi-billion-dollar series of businesses inside the company that need advanced behavioral analytics. If you can think of any of our suite of products, everyone wants to know how users are working on the systems and using those systems. So understanding those behaviors is incredibly important. These capabilities have been built, and these types of solutions are being built on top of SQL Data Warehouse, and we partner with internal teams that build those solutions, okay? Especially during development phases of some of these types of products, because if you have these enormous solutions that Microsoft requires to run its software, that value can percolate through for customers as well. So we get some very important feedback during early development cycles with internal teams for both performance, quality, and experience. So one of the teams that we've been working with closely has been building an internal tool to help users perform their own interactive product analytics. And this is all at massive scale, hundreds of terabytes of data, and trillions of rows. So this team is already using the Optimized for Elasticity team, performance tier, but they were keen to take it to the next level. They wanted to know what else we could bring for them, and they were really pushing on us to kind of push the boundaries of what we could provide to them in terms of a new experience. Okay, now given their use of the system, they were a great partner for us internally, and they've been a wonderful advocate for us across Microsoft for the advocacy of our solution. And the reason they look at SQL Data Warehouse so closely is because they have evaluated a number of other big data solutions and realized that there are a number of major limitations in those solutions. The first is query language. SQL as a language, as I say, was incredibly pervasive, and it has this kind of zero cross-training capability that is available straight off the bat, right? It's a very, very accessible language. Most people know it to some level and can run at scale. The second thing they notice when they look at big data solutions, they could see that quite a few of them are adopting SQL as a language, but they don't really have SQL as an engine, and they don't have the rich functionality that SQL Data Warehouse has. When it comes to actually running batch queries or big queries in these big data solutions, many of them have still a very batch-orientated paradigm. And so the next thing that they realized is that you actually have quite a lot of patience for running major big data solutions, and your cost of curiosity is actually quite high. That means that if you want to explore the data and find a problem, you'll submit a batch into the big data solution and then sit around and wait around for that solution to come back to you. Now, there are obviously advances that are coming into that space, but you actually need to have quite a lot of, there's still quite a long way to go when you compare that to a SQL engine-based product. The other thing that they found was that you actually need to have quite advanced skills to get into the world of behavioral analytics in a big data solution. It's nowhere near as accessible as SQL is as a language. And so those three things actually made them choose SQL Data Warehouse as their platform when they got into this. Okay, so what their tool does is it provides an easy experience for an analyst to build these conversations, these scripted dialogues for analytics, and enable customers to get in an interactive way without the need of developers or engineers to actually build them any custom code to be able to get out the insights that they need. Okay, Without Azure Data Warehouse, it's not possible for them to actually get the scale that they want, the responses that they want, and the richness of the functionality. And they were very, very happy when we showed them the optimized for compute here, because they were able to get a significant performance boost based off of that local caching architecture. Okay, so the scenario we're going to talk around is really in advanced behavioral analytics is really, if you think about like a company website or something like that, you think about how engineers and site owners, business site owners, want to be able to understand what are users doing and why they are doing it, because they want to improve the customer experience. So one example of this that I've seen quite a lot personally is retail checkout scenarios. You've seen a lot of people actually innovate in the checkout basket experience because they want to make sure conversions are high. Okay? So if a developer can improve that checkout experience and understand why people basically abandon their checkout, it's both good for the customer, it's good for, because the customer is no longer frustrated, but it's also good for the website. It's a win-win for everyone. Okay? Now, one specific way of doing this is through a specific scripted analytical channel known as funnel analytics. So in funnel analytics, we track events that lead to the completion of a goal. In this case, checkout, right? Do I succeed in the checkout? And if you think about your checkout process, you have a step, next, 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 done. And over time, you know, you've seen people do things like removing blockers in that checkout process. So you'll see lots of people don't require you to register in order to be able to check out, right? Boundaries are being removed because they have seen that customers abandon the checkout process if they get frustrated, and that's not a good experience. Okay? So typically, the way a funnel works is at the top of the funnel, that's the way you come in, right? The funnel is very wide. As you go through the steps, if you think about it, you're adding maybe your billing address, your delivery address, credit card, etc. People abandon as you go, and so the funnel narrows. Okay? With the last step being the actual goal. Now, our goal is to make the funnel at the bottom as wide as the funnel at the top, right? So that actually as many people as possible get through. Okay? So you can use this funnel analytics to look at the conversion rate of people entering at the top versus people that actually transact at the bottom. All right? Now, you can see in this example, okay, that this is a contrived example, but you can see that everything's sort of okay-ish at the top, okay? But as we come down to step 4, badness is happening, right? And we can assert that we're looking at, say, the funnel for Q4 sales, and there's something that's happened in Q4 that has meant that we are not doing what we're supposed to be doing, right? We have changed the funnel in some way that may be causing us a problem. And then when it comes to step 5, it gets worse still because, again, the number of people that are coming through to the commit point and actually transacting is low. So immediately, by looking at this type of analytical visualization, an analyst is able to see quite clearly that they need to go and investigate steps 4 and steps 5. Okay? So they could dig deeper into what's going on. Now, to combine this funnel analytics, they may also have a second type of analysis that you can actually apply to this problem. And that analytics is known as cohort analytics. Right? This is where we subdivide the top of the funnel into groups of users that have some commonality between them. Okay? So this can also yield some very interesting insights. And this is cohort analytics. Okay? Now you can look at this, and this is the 4 quarters for the year. Our funnel was for Q4. Okay? Now you can see that actually by splitting the users based on how they came into the site, okay, I'm able to get some insights into how successful different entry points are compared to my funnel. And you can see that actually there are two types of source that are more successful than others, right? There's Facebook on the one for Facebook ad. Maybe the ad is more compelling. Maybe we're putting more money into that advertising. But also, you're seeing this stellar rise of our new app, right? So the app has grown and grown, and everything's looking peachy up until the end of Q3. Now Q4 comes along, and you can see that actually everything has taken a hit. And so by splitting into cohorts, we can see what are the most successful things, but also the general pattern of whether or not things have succeeded or failed. Now, even then, you can still see that the Facebook app and the Facebook and the app are still generating the most compelling results for us. Okay, so what we would then do is take those two analytical results and be able to do our own analysis on the Q4 to be able to work out what may have changed to, of course, such a dramatic change in the user's behavior. Okay, so these are the two kind of principles of behavioral analytics, or two subsets of analytical capabilities. All right. Now that we have that kind of analytics in place, or those concepts in place, we can look at the kind of a demonstration of it. Now, the reason why this is an important type of analytics is because, especially in the world of retail, like they say, time is money, right? And so being able to tune kind of campaigns based on how successful certain things are running online in real time is very important. So what we're going to do is actually go and look at a couple of queries in a second, okay? In these queries, I have loaded into two parallel systems over 100 terabytes of data. In the first instance, we're going to have an optimized for elasticity solution, the other one optimized for compute. Now, what I've done is priced the systems so they are priced the same. They both run at the equivalent price of 6,000 data warehouse units, and so that you can see the difference in terms of performance. Okay. Now, funnel queries are pretty expensive computationally to run. Okay. So I'm just going to eternal search for the mouse pointer. Okay. So this we're going to run on the elasticity solution. Okay. Right, so this is going to combine, this is a funnel query. The funnel query starts at the top of the funnel, and then it folds the data multiple times to create the funnel. Okay, and it's blending that with these cohort queries. You can see it's using CTEs to build this, and you can see that this query is quite involved as it goes through. Okay, so it's a non-trivial query in that sense. So I'm going to execute this on the optimized for elasticity, and now I'm going to move over and execute it on the optimized for compute. And it's going to want. So the optimized for compute is done in 2 seconds. Optimized for elasticity should take about 30 seconds. Okay. Either way, you can see the two queries One has taken 2 seconds. The other one is going to, well, should take about 30, 45 seconds, something like that. The difference is a 10-fold difference in performance, because the difference of having the data locally cached with a higher degree of local computational power gives us that, that solution. So you can see there, on that occasion, it took 53 seconds to run that query to bring it in, versus the 2 seconds running on the optimized for compute tier. Okay? You can see that what you're getting there is a significant difference. If you imagine you are the end user wanting to run a campaign and being able to tune your analytics and being able to get that data and understand what is going on in your system, having that hot data close to the CPUs is going to give you a dramatic difference in your compute performance experience. So with that, we're just going to quickly flick back and I'll start talking about how you can now maximize the performance of your solution. Because in order to do that, you need to know how to make the most of the column store, right? The column store data is what we're caching when we do this, okay? And a column store in SQL Data Warehouse runs over 60 distributions. You can think of those as shards, if you like. And we contain one column store table per distribution, all right? So each distribution has one table in it. Now, the column store itself starts life as the data that we ingest, right? So in the world of user behavior and analytics, that data would be event-based data, okay, or clickstream data, you might have heard it, but it's data. We break that data up into row groups. The row groups can be in one of 3 states: open, closed, or compressed. When it hits the compressed state, it is in column store format. That row group is then subdivided into segments. A segment you can think of as a column, okay? Each segment is completely separate from the other from each other, right? So they are completely separated. And these segments are what we actually store separately from the actual data files of the SQL Server database. We store those separately, and we bring those up into cache. That's what we're moving into cache, okay? Now, those segments are then compressed and pushed into the column store format. Depending on the data types that you have and the nature of the data that you have, that data will be compressed better or better than others, right? So depending on what data is there. To assist with strings in particular, we also have the notion of dictionaries. Dictionaries are either primary or secondary dictionaries, and these are used to substitute the strings for integer-based values to assist in the compression. Okay? So there's some basic kind of column store data. Now, as you saw, what we were doing is some very big scans. We scanned over 100 terabytes of data. We scanned trillions of rows to get us to that point with that 2-second query. Okay? So the column store itself actually has to do a few things when you're actually scanning data, right? It actually has to combine the row groups in their various states, the compressed row group, the delta stores, or the open row and closed row groups. They have to be combined together with a delete bitmap. A delete bitmap is because columnar data, because it's compressed, is actually difficult, is less efficient when we update and delete it. Okay? Because when we update and delete it, the deletes are actually logical deletes, and we hold that logical delete in the delete bitmap. That has to be brought together with the open and closed row groups, which are those boxes in red. Okay? So how do we improve the performance of scans? We can improve the performance of scans by sizing the compressed, by making sure that we have the maximum number of rows in any given row group. A row group can hold specifically 1,048,576 rows, which tells you 2 things. Okay, the first thing being that an engineer came up with that number and not any kind of business marketing guy, right? Because it's 1,024 times by 1,024, right? That's the first thing. The second thing is that the more you put into the row group, that is our unit of compression, and so the more rows in there, the better the compression is going to be, okay? So the second thing that's going to affect your performance is how many open row groups you have. Open row groups are where we hold any delta changes, updates and deletes, and any kind of small singleton inserts and single batch statements. We collect those in open row groups until such time as we're ready to kind of compress those because we've got a critical mass of data. The last thing that's going to affect scan performance is a delete bitmap. At the end of the day, we have to make sure that the results are correct. So when we take that logically deleted data, we actually have to kind of remove those logically deleted rows as we scan the data to bring it in for your query. And so the size of the delete bitmap can impact your performance. So that's one of those scenarios where you're going to want to kind of optimize your bitmap. Now, the inserts themselves, okay, it depends on the batch size. We would encourage you to use a large batch size. Each row group, if you have over 102,400 rows, again, engineer, then you will go straight into column store format. If you have less than 102,400 rows, you'll go into one of those open row groups, okay? Now, the open row groups, as you get more and more data into them, once you hit the maximum, those open row groups will be marked as closed. You can think of that as like a store open and closed for business type scenario. And then those will be automatically migrated into column store format, okay? The goal is to have the majority of the data, obviously, tightly packed into those column store formats. Now, because, as I say, updating and modifying column store data is more of a challenge, we use this logical delete pattern. So if anything is actually inside the column store, if you try and delete data that's in the column store, we convert your update into a delete and an insert, okay? i.e. we will logically delete it and then physically insert a new updated record into the open row group. So if you're doing a DML pattern on your fact table, if it's a heavy one, then you're actually evicting rows from the column store format and you're pushing them out into row store format. So one of the things that you will want to do is to kind of optimize your column stores if you are doing that, and you may even change some of your workload patterns to match that. Now, there are some catalog views you can use for monitoring this, and I will show you some queries, and most of these are documented in our product documentation that you can use to actually review the catalog, okay? So the second thing we talked about was actually the ability to kind of maximize your compression. The better the compression you can get on the data, the faster you can go, because the fewer IOs you have to perform, okay? So there are a few compression performance factors, okay? The first is that if you over-partition your table, then you will impact both compression and performance. It's important to realize that when you are partitioning a distributed table in a scale-out system like SQL Data Warehouse, that you already have split the data 60 times before you even start, and I'll show an example. The second thing is that the column store is a memory-intensive beast, and compressing data is a memory-intensive operation. Now, one of the factors I told you about is we have 2.5 times the memory in DW in Optimize for Compute. So you can actually use that to your advantage for compression rates. And then the last one is that really maintaining the CCIs themselves is what will give you the tip-top performance, okay? And we'll talk about how you can do that at the end. Now, when you have a table in DW, you can partition it using syntax like this. It's actually in some ways more friendly than SQL Server because you don't need to go and create schemes and functions. You just set what the boundary points that you want. So in this example, we have a range right, and I have two partitions, 2016 and 2017. And so you end up with 3 partitions that cover the range right scenario. OK? So now those column stores have been split because actually those row groups themselves cannot transcend a physical partition. And so the data in it would be split. The easiest way to have this conversation is to put it into a concrete example. And if you're building solutions like this, I strongly recommend that you do something similar to this. So if you can look here, I have partitioning granularity on the left, and for a 60 billion row table that's got 3 years worth of data in it. So if I do no partitioning at all, that 60 billion rows will be divided 60 times, so I'll have 1 billion rows in each table. Okay? That means that with 1 million rows per row group, I will have 1,000 row groups for each partition, i.e. the one partition that I have. Now, if I decide to split that data yearly, I would end up with 333 million rows per partition, or 334 row groups. By quarter, I'm down to 83 million. By month, I'm down to 27 million. By day, I have less than 1 million. Now, everybody starts at the beginning and they think 60 billion, that's a really big number. I'm going day level all the way. Now, in this scenario, if you look at that, 1 day is less than 1 full row group. And so my compression rate is going to be impacted. My performance is going to be impacted, because if I was then trying to scan across partitions, I'm now going to have to subdivide all of my cores across those partitions as I scan that data. So the reason I mention this is because SQL Server customers in particular, by far and away, like by a country mile, the most common partitioning strategy is by day. And so when using a distributed system and you want to maximize the compression, get all the benefits of the column store, all this, right? You're going to want to revisit that partition strategy, right? You're going to want to get that number higher, and you want to focus more on the business problem, i.e., how are my users trying to query this? Do they query it by day, by week, by month, by quarter? Think of partitioning as much as a data management unit of operation, rather than purely as a performance technique. Now, I mentioned it in the resource class. You have 2.5 times more memory, but you also have a new type of resource class, and I chose today to talk about that, and I've shown a subset of that resource class here. These new types of resource classes are called static resource classes. Now, in DW, we start with 250 megabytes of memory per distribution, which gets you up to the 15 gigabytes per query. With optimized for compute, that's a 2.5x uplift on what you get with the optimized for elasticity, which means that you can actually do a lot more. The static resource classes are great because they give you very fine-grained granularity of control over how much memory you're allocating, and therefore how much concurrency you are kind of using in the system. Okay, so the summary of the memory utilization is here in this calculation. I'm going to leave it here for reference. I also have these views that we publish online that give you all of the data behind these calculations, and I'm going to demonstrate the views to you in a second. Okay, but the main thing here is that in order to build good quality row groups, there are a few things that you need to take into consideration. The first is how big is your warehouse, right? The bigger your warehouse, the more memory you can allocate. hopefully that follows normally. The second thing is which resource class you're using. As you saw in that graph, resource classes allocate more memory, the higher ones you use. The complexity of the load or the query. You know, at the end of the day, how big is the memory grant that the query that you require? And we're going to look at it from the point of view of an index rebuild in a second. Whether you partition or not, if you partition a table, don't forget that your minimum unit of compression is going to be a single row group. And then the degree of parallelism that is applied to the query. Now, if the memory required exceeds the amount of memory available, we will actually trim the row group, i.e. we will prematurely compress it, i.e. you will not get the best compression that you can get. The row group won't be completely full. We will have trimmed it. Now, to give you an idea of when this trimming might occur, I've come up with a couple of examples. Memory grant example number 1 shows a 10-column table. And here you can see where the lines are for elasticity and compute. Okay? You can see that what I've done, each bar represents a different configuration of a 10-column table. The first one on the far left is all integers. As they move over, they have more and more and bigger and longer strings in them. Okay? You can see that by default, the compute in the very smallest configuration has more than enough memory to cover all of these kind of common scenarios. Now, as you go into the 30-column table, you can see that there's still a little bit in each one, depending on how many strings you have. As a general top tip, if you have a massive fact table, and I mean like massive, hundreds of terabytes type thing, you're going to want to optimize out strings from the fact table. It's not necessarily a good plan to have strings in a fact table of that size. But you can do it. It is more memory intensive to have them there, especially as you compress it. So you can start here with compute. Now that's the entry point. Obviously those numbers go up, and we can actually allocate lots of gigs of memory. You don't need to worry about that. It's just where the entry point is, how much you have to worry about it. Now, in those strings, I talked about dictionaries. Dictionaries come with their own pressure. Because we actually maintain a max on the amount of size of any one given dictionary. So if you have high cardinality in your data in a string on a fact table, you may run into this notion of dictionary pressure. I'm going to show you a couple of examples in a second. Now you can see all of this data in these with a couple of DMVs. They have very long names, again, very descriptive, but very long. And that trim reason is the thing that will tell you whether or not you've hit a problem with memory. Now, there are two ways to resolve the compression. One is to allocate more memory and then either issue a reorganize or a rebuild of the index or the partition within that index. And I've given you the summary here of when to use what. Okay? As a general rule, we try and encourage customers to start using the reorganize more than the rebuild, because the rebuild basically does the whole thing, whereas the reorganize is both an online operation and it doesn't actually, it's more selective in how it approaches the problem. So to show you a little bit, I've got some, going to go back to demo land before we kind of conclude the session. So let's close those two. Now I'm using some tables that I've created earlier to do this. And these views that I've got, this one's called VCS mon row groups. It's basically going to monitor those row groups for this table. And this is a memory grant table that's got 10 columns, 10 long strings in it. Okay? And there's about 60 million rows in it. Now, if I run this, I can look for memory grant pressure here. Sorry, excuse me. Let me... By querying the distributions, I can actually see that I have memory grant pressure because I actually have 500,000 rows in each one. I deliberately picked 60 million rows because then I can actually look at the highest intensity scenario. Now I can then go and look for those trim reasons to see what might have caused this problem. And when I go and look here, come across, I can see I hit a memory limitation. Bulk load just means it got to the end. But the memory limitation means I got memory pressure loading this table. Okay, so what I can do is run this next view that actually says, well, how much memory do I need? I need to have a minimum of 312 megabytes of memory per distribution. Now, there is nothing more tedious than watching an index rebuild, so I've taken, in British style, a Blue Peter example, i.e. one I prepared earlier, to show you what would happen if I rebuilt using a higher resource class with that amount of memory. And you can see now I have a 900, almost a million rows in the row group, and I only have one row group per distribution, which is what I would have expected. By contrast, if I ran the same basic scenario on the optimized for compute, you would not see a need to have done this in the first place just because we had more memory to begin with. If I look at the memory grant trim reasons on this table, you can see they're all in compressed form. They all have this bulk load reason, which basically meant I ran out of rows, so I ended. Okay, so that's it, and it's in its full state. Now there's that slightly interesting one, which is the dictionary pressure scenario. So in this case, what I've done is I've moved everything over. You can see here's my table. It's got all the 10 strings. But you can see I've been a bit cheeky. I've increased the last one up to a varchar 1000, and I've created a high cardinality row in that table. Now, if I was to go and run this against memory grant, I can still see I need that I'm still getting told I need that 312 megabytes of memory. But if I actually go and look at the health of the column store, I can see a different story. I actually have 19 row groups, and each one has less than 50,000 rows in it. If I then look for the trim reason, I can see the dictionary is causing me a problem, i.e. I fill the dictionary prematurely. Okay. Now, how do I find out which one? Well, I can use a query like this that's leveraging these views. It's all up in our documentation. And when I run that, you can see that I have almost 1,200 dictionaries for one column. And so I can now look across. I can see that column is column 10. So I can now identify that column. Now, what I would do in this case is I would take that column and I would separate it out from the rest of the index because that dictionary size is too high. The cardinality is too high, and the only way to really address that is to separate it from the rest of the table. Now, if I reorganize that table, I'm not going to get the benefit. Similarly, if I have a partition version of that table, you can see that I have more than 100,000, but I have it split. This partition table has a number of partitions in it, about 8. And I can then look at a query like this to review the number of rows in each partition. And I can see here quite clearly how many rows I have. Unfortunately, that then is going to give me some problems when it comes to trying to compress this data. I could actually get almost all of this data, as we've already seen, into a single table. And you can see that when I rerun that here. So this is a classic case of an overly partitioned table. Yeah. So that's what I was saying about the partitioning affecting the compression and therefore ultimately the performance. Now, most of those scenarios, with the exception of the dictionary pressure, all work much better, much cleaner on the optimized for compute layer because we have much more memory to start with in the first place. Now, just to wrap up the session, the optimized for compute tier has up to 10x improvement in performance of individual queries, and generally what we've seen is a 2x price perf improvement across a given workload. And that scenario I showed you, the demonstrated, the analytical one, I highlighted one of the 10x improvement queries. We also have 5x scalability. We're now able to run at 30,000 compute data warehouse units, which is our unit of scale and normalized performance. And that's what percolates through onto the as a line item on the bill. We have more flexibility that we can provide to you with the additional resources that are available to you. You actually have more temporary storage on the node itself, and you have more memory on your queries, and you have more compute capabilities generally. This can be used in a number of different ways. I've shown you a couple specifically around optimizing your column stores in the first place. You have all of the elastic functionality, but as I say, it's more about as you scale the system, as you add more data and you want to scale it and grow it, that's more its use case in the optimized for compute pattern. And as I say, it's all measured in compute data warehouse units as opposed to simple data warehouse units that you'll see in the elasticity tier. To maximize your performance, define your tables as column store because only the column store segments are cached. So if you really want to make the most of the optimized for compute perf tier, then I strongly recommend that you define your tables as column stores in the first place and maximize your compression, because the more you compress the data, the better you've got your compression, the more full the row groups are, the fewer IOs you'd need to do, the actual it's a better utilization of the cache. Everyone wins when compression is at its tip top. Reducing your resource class. What we've seen, customers who would run on higher resource classes on optimized for elasticity, this is a bit of a more advanced point, but as they've gone on to those higher resource classes, you actually can step down in many cases when you use the optimized for compute tier. And also, if you're doing that, you might as well also move over to the static resource classes, because those static resource classes give you the fine-grained control that you need when running, and it also means that you'll be able to run at even greater concurrency levels within the system. Okay, so that's everything I have. I'm over. So I just want to say thank you all for attending the session. I appreciate all of your attendance and feedback, and I hope that you enjoy the rest of your conference here at Microsoft Ignite. Thank you very much.